All right, so hope that everyone can see my screen now. Yeah, now it's my part. I'm going to introduce the latest features and innovations in the binary-based analyzers in the aiCube framework. So the features for aiT, StackAnalyzer, TimingProfiler, and also the ValueAnalyzer in 1604. And I've here a short overview about these latest features. And the first of them is what we call the automatic variable initialization analysis. It's a completely new process which combines the value analysis with all other analysis. I'm going to introduce that in more detail in a second. The next point is that we made a big step towards C++ support in this release. Of course, we also introduce new AIS2 annotations that I'm going to present to you. And last but not least, the graphical user interface has, of course, also evolved in this release. So let's start with the first point, the automatic variable initialization analysis. What is the problem here? Well, the problem is that you have very often pointer variables or just data variables initialized outside of the actual task that you're going to analyze. And so in the task analysis itself, this initialization data is missing, which may lead to the common problems like unresolved computed calls or branches, but also unbounded loops and recursions. And the idea is now that you may have a separate value analysis of initialization sections or code parts and transport that initialization data to the actual task analysis. And that's what I'd like to show you right now. I've prepared a small example here in the aiCube for PowerPC. I have here a project that has several TimingProfiler analysis. And especially here, this 5 millisecond task, which simulates a CAN message processing, lacks or has some unresolved computed calls. If I start the analysis, you see that we have an unresolved computed call in the 5 millisecond task main routine and one in the OS error hook. And if we have a look to the source file, we see what happens in there. So at that point, we have a call of a routine handler. And this is done via some variables, via some pointer, which is called register message handlers. And depending on some message type, a different handler here is called. And if we have a look where this registered message handlers pointer comes from, well, it's obviously set somewhere outside of the 5 millisecond task, which we are analyzing, and it is set here in a separate initialization task, which with the name init here. You see here the variable, the pointer is set to the address of a message handler table. All right. Then we have a second computed call here in the OS error hook, and well, it's very similar here. We have a registered error handler, and this registered error handler, again, is not set in the task directly, but also here in the initialization task. So it would make definitely sense to analyze that initialization task separately and transport that initialization information to the actual task analysis, right? And that's what we have enabled with this new initialization analysis. For that, I introduced a value analysis item starting here at this initialization task. And we also have to say, well, we want to collect some information during that initialization task. And that's expressed by AIS2 annotations, which is named collect initialization. And here I mentioned those variables I'm interested in for the initialization data. And then what I also have to do is to say inside of my task analysis, we have introduced a new field that is called dependencies here. Yeah, we have to mark from which analysis This task analysis is depending on, and in this case, it's from our init value analysis. So I tick the dependency here, and now when I start the analysis, it will of course first execute the value analysis of the initialization. Then it will generate fully automatically aiT2 annotations when it, of course, only if it has found initialization data for those variable, and it will also comment that here. You see for the registered error handler, it found some initialization value, which is that one, and it transforms that into an aiT2 annotation. The same happens here for the message handler pointer variable. And those annotations are automatically transported to the task analysis. And by using that, you see our problem here with the unresolved computed calls have vanished. And both of them are automatically resolved. And without any further computed call annotation required by the user. So this is the first very nice new feature. So let me switch to the next category. That's the advanced C++ support. And we have made a very large step here in better support C++ based binaries, not only in the visualization, where we can now show C++ or symbols in the graph in C++ style. We also improved the dwarf debug view a lot, because we can now show here C++ class information and also inheritance information with all these members, C++ members listed there. But also in the aiT2 annotations, we are now allowing to express function members of C++ classes directly in the annotation. And I'd like to discuss that now with you. So you all know that C++ has a big advantage with this object-oriented style. You can easily have type polymorphism. You can have base classes that you want to derive, and in the derived classes, you may override or overload some of the members. And to do that, to enable that, you need virtual function members. And virtual function members can, on binary level at least, it can no longer be resolved statically by the compiler at compile time. Instead, the compiler introduces computed calls here via so-called V tables to determine the right class member during runtime, depending on the actual object type, right? And the consequence is that whenever you have a virtual member called at runtime, you will have in the analysis a computed call, which the user has to resolve. And these computed calls are still present in the latest release, but it has become much more convenient to resolve them. And we also provide much more information about that computed call. So let me show that to you in a small example. I've prepared here an analysis project. In the source file, you can see here we have a class that is called prime. This prime class, of course, has some constructor, some destructor, and it also comes with here this function with these members f. The first one has the signature. It takes the parameter double parameter x, and it returns void. And this is fully implemented here. So this is not a virtual function. It's a a non-virtual function or member actually. But then we have also two virtual members, also named f, but with a different signature. The first one takes just one integer parameter and returns void, and then the second one takes two integer parameters. You see also here a difference. The first one of them, the first virtual member f here, is also implemented. provides an implementation here. The next one is a pure virtual function. So that means it comes does not come with an implementation. So this is the base class prime, and from prime we derive the class A now. And A well, overrides the virtual function f here that takes just one integer, but it also overrides the function f that takes two integer parameters. Yeah, and so on. We have another class B that again is derived from A, and here again we derive the function member f, but that time only those with two parameters, and so on. We also again have leaf A, B, C, and D, all derived from the class B, overwriting f again. So you see a big inheritance tree here, and this can be visualized very, very well in the new dwarf debug view. You see that here, for instance. First of all, we have here introduced a new type T, showing that this is a class type, and it gives the overview about the class values, the class variables, and the members. And you see here, for instance, our f members, all these three which are available, one with a double, with one integer, and with two integers. What you can also see is that the double one here has an implementation, obviously, because the address is an absolute address. That means we have a representation here that has been implemented. The second one as well, you remember, we have an implementation for the first virtual member f, but the last one here is just a pure virtual member. That means we don't have an actual implementation here. That can be seen because you just have an offset here into the V table. Yeah? And then you see that prime derives a class that is called A. So A is derived from prime, and this is visualized here by that arrow and by this marker that it has been derived. I can double click here and I see the class type specification of A here. And what you see here is that F, of course, those two F variants which were virtual have been overwritten here by two different implementations, and so on. All the other classes, of course, are also derived from a respective B. So that's a big advantage now that you can see the class structure just from the binary and just from the debug information. You don't actually need source code here. You can just have that overview with the binary information. All right, so let's have a look to the analysis here. And well, no, we just let me first show how the source file here ends. We have a small main program. It declares 4 objects here of type leaf A, B, C, and D. And then we have an object list with 4 elements, namely these A, B, C, D objects. And this list is of type prime. Or prime pointer, basically, and because we have here different types and we want to put them all together in just one list. And then, depending on the program's argument, we select just one arbitrary object out of that list, and we apply the 3 different functions here for f. The first one with the 1 integer, with the 2, and with the double value. And what you can imagine is, well, the last one will be statically resolved because this is a non-virtual function. This can be statically resolved during compile time. But for the first 2, we will probably get 2 computed call problems here. So let's start the analysis. I've prepared here a small stack analysis, and if I start them, that's exactly what we see. We will get 2 computed call warnings, and the last call for this double value is resolved properly. You see here, by the way, also this nice improvement that we can now visualize the C++ symbols in C++ style. So we visualize here that the routine F is contained as a member in the class prime, and we also visualize the signature if it's not or it's not unique in that case. So, but we have these two unresolved computed calls, and we have to get rid of them. So let's see the first computed call in the graph. It's at that point, and you remember the source file. It's the first call of f with the parameter 32. We would have to resolve that, and now that's a really big improvement. Now you can resolve that quite easily in the aiT file by just one-liner, basically. I just for a better overview put that into more lines. You say, well, let me resolve all these computed calls inside of main by just applying the f member of the basic routine prime. Or the base routine class prime. But what then will happen is the analyzer will search along the inheritance tree all matching implementations for this f member. Yeah? And you will see if I apply that annotation here in the graph, you see the following. It will apply these call targets. It has found, well, there is some concrete implementation, the AbsInt. Then we have an implementation in the class A, in the class B, and leave A, and so on. You will see, of course, we have kind of overestimation here because we also apply those variants of f with the signature that we have two integer parameters. This is of course not applied at that point, but it makes well, you still have a safe result. You can even do that better, which I'm going to show you in a few seconds. The second one is also resolved automatically here along the inheritance tree. Of course, it also applies the variant with just one integer. What you can also do instead of resolving that at once, you can of course also say, well, let me resolve them separately. Yeah. So let me repeat the analysis quickly, and then let me copy that annotation suggestion. And what you say now is, well, we know that at the first call, we want to resolve that with the class prime and f, but we want to restrict that to just the signature for those with one integer parameter. Yeah? So that means, and this can be restricted here. And for the second call, we know, second computed call, we know that we would like to resolve only those with two integer parameters. So let's start over again the analysis and see what happens. Now we have a most precise resolution of the two computed calls. The first one is just resolved by using those members with just one integer parameter, and the second call is resolved with those with two integer parameters. Yeah? The problem why the tool is not able to resolve them completely automatically is because it does not know actually on binary level at that point which member exactly, so which member of which type is called here, and that's what the user still has to do. But it's very easily. You see in the code, well, you have a member f from an object, and the object is of type prime, and you'd simply have to say in the aiT file, okay, then let's resolve that with prime f, and if you even know the signature here, you can provide it as well. And then the analyzer will do everything automatically for you, resolving it along the inheritance tree. I think that is a very big or a great improvement towards C++ support in the aiT tools. Okay, let's come back to the next feature I'd like to show you. The next new ones are the aiT annotations, the news. We have here the first is that we can now express a specific call stack that you want to mark in feasible. You can say, if you have a call stack, I'm coming from routine A via B and C to a routine D, and I'd like to make that call stack infeasible, then you can express that now with the annotation routine D infeasible call stack A, B, C. And only then, if I come over that path to D, I will make routine D infeasible. And from all other contexts, D stays, of course, executable. That's the first new AIS2 annotation. Then, second thing here is that we introduce guarded annotations with the release 1604. You can now specify, or you can now apply an annotation depending on the analysis type you are currently running. So, for instance, if you have just a global AIS file, and as you have seen here in our project, we have different types of analysis. We have StackAnalyzer, we have TimingProfiler analysis, and if you want to say, well, let me exclude some code from analysis, here the error hook, but only if I'm running an analysis that is not of type StackAnalyzer. That means for StackAnalyzer, I'd like to consider error hook, but for all other timing analysis, for instance, I want to exclude that error hook routine. So this can be done with the new qualifier analysis type and with the new guards. These guards can be more generic. You can express an arbitrary Boolean expression that is allowed in AIS2. Also inside of this guard, you can, for instance, say, well, if I'm currently analyzing my 10 millisecond task by expressing here that my analysis start address equals the address of the task with 10 milliseconds, only then I want to exclude the code. For all other analysis with a different ID, with a different entry point, well, I don't want to apply that annotation. So this is guarded annotations. And then, last but not least, in the AIS2 improvements, we also introduce the value patching annotations, the enter with and exit with annotations, now also for call edges. You can say, if I'm entering memcopy through the edge coming from routine handle input, only then I want to patch my register content for R5 to the value of 80. From all other entries, from all other call sites to memcopy, I don't want to apply value patch here. This can be realized now with the call edge annotation, which we call routine calls to enter with and exit with. All right, that is about the AIS2 latest features, and then the last section I'm going to show you is the graphical user interface improvements. And here we have the first thing I'd like to show is the disassemble all and call graph all in the section information here. You now have two new entries that are called disassembly and call graph. And let me just do the call graph. This one will go over the symbol table of the binary, and we'll have a look to each symbol that is marked as a routine in the symbol table, and we'll decode that from that symbol entry and generate call graph at that point. And this allows quite good to have a complete overview of the binary. So maybe you will have unresolved computed branches or calls, and doing that you can collect all of them at once, and well, that might help to have a better overview. So you see, you have now individual graphs for each of these symbols that we have decoded. So you see here, for instance, for QSort, we have a different graph. We have, and you can also search for routines. Of course, my milliseconds task, 5 millisecond task will be shown here, and so on. So this is the call graph all, and the same functionality is available for the disassembly all. And a big advantage is, of course, that you can search over all graphs with the search button here. Oh, all right. So then we have a new memory usage analysis, and well, if I'm starting here in analysis, I can open the memory usage box here. Unfortunately, this analysis is that fast and needs not that much memory that you don't see anything here. But in realistic, industrial applications, where you have much more memory usage during the analysis, you will see here some graph that is evolving along the memory usage inside of the tool. So you can monitor basically the memory usage here. All right, and then the last thing I'm going to show to you is the AuTI file importer in the project. You can have, if you have a new project, if you start setting up your analysis project, you can now import the project specifics from an AuTI file specification. So this is from the debugger file format. When you have an OSEC AutoSAR system, you typically also have AuTI files, and you can say, well, let me import data from your AuTI file. Let's do that here in the example. I've prepared some AuTI file for the scenarios here, and then I also have to provide the binary file, and then I can say import, and then it will the analyzer or the graphic user interface will automatically generate an analysis project file here with 4 entries in that case, 2 different tasks and 2 interrupt service routines, but it will also generate result combinations. So because it knows from the AuTI file which tasks are running on the same stack, sharing the same stack, and how can they be interrupted by different interrupt service routines or tasks. So in this case, both tasks here, 10 and 5 milliseconds, share the same stack, but they can be interrupted by an interrupt service routine, and this will be automatically generated, that formula. And even more, it will also provide an expected result, which is also contained in the AuTI file. So this is a limit for the stack usage, and this will be also applied in the result combinations. Yeah. All right, so this is the AuTI file importer, and that concludes, I think, the features I wanted to show you today. So if you're interested, I want to have a look over more detailed overview for the release notes, please be referred to our website. And now we have some few minutes left if you like to ask some questions to Astrid or the aiCube release. Please unmute yourself and ask questions.